Okay, so problem number 2 is going to be I'll say a simple shear problem. Shear force is different from normal force. Normal force is acting perpendicular to the cut. Shear force is in the plane of the cut. So I think sometimes it's helpful to cut it. Go ahead and shear it. Go ahead and fail it. Go ahead and see, okay, what would happen if this punches out? So let's look at this one. We've got a suspended rod supported at its end by a fixed connected circular disc. If the rod passes through a 40 millimeter diameter hole, determine the minimum required thickness of the disc needed to support the 20 kilonewton load if the maximum allowable shear stress is 35 MPa. That's a lot. All right, but visualize it, and they actually did it for you here. May not do this for you, but visualize if this failed, if this cut out, if this sheared, how would it shear? What is the cut? And so here is the cut would be the circular, the circumference, almost like a cylinder, the surface area of a cylinder, would be the cut that the shear force is acting over. All right? So, tau is V over A, very simple equation. In this equation, we actually were given tau. The V is 20 kilonewtons, and so here we need to think about and figure out this area. This is the area, not necessarily a cross-sectional area, sometimes it is, but it's the area that it fails, the area that the shear force is acting. All right, so if this is 35 MPa, if the V is 20, I would do 20,000. Here's a side note, what I like to do. MPa is Newton over millimeter squared, and that's how I do most of my stress equations. Pa is Newton over meter squared. I guess kPa would be kilonewton over meter squared, but a lot of times everything's in millimeters, and so and most of stresses a lot of times are in the MPa range, so MPa is Newton over millimeter. So I've got MPa on the left hand side, I'm going to have newtons on the numerator and millimeters squared on the denominator. All right, so what is the area? What is the area? Do you see that the area that this fails, the area that the shear force is acting, is this area? It's like a surface area of a cylinder. I like to think of this as if I could find this circumference, right? This circumference would be pi times diameter, 40 millimeters. That would be the length of that circle. And then it is, times the height of that, times the height. That was actually what we are trying to find right here. So that's it. It's very simple, right? If you can get everything in the right place. So here I would get the thickness, 4.55 millimeters. That's the thickness that would cause a stress of 35 MPa. I'm not really doing factors of safety, but with factors of safety, I'm definitely going to want to make that a lot thicker than just the minimum 4.55 right there. Okay? Shear stress is V over A. Shear force over area. Think about what area the shear force is acting. Think about what area the shear force is acting. Think about that by going ahead and failing it, going ahead and shearing it off. Look at those pin and bolts problems, because bolts, let's talk about those. Bolts, if we've got, one plate here, one plate here, one plate here, this is pulling this way at some force. This would be pulling this way at some force by 2. If this were to fail, what area would this bolt fail? I could see it failing, right here along this circular. So for bolts, it's not necessarily the area of a cylinder. Bolts would shear this way, and it would fail. That area would be the circular cross-sectional area of the bolts. Many times for bolts, the area we're looking for is the cross-sectional area of that circle, pi r squared. All right, but anyway, look at a few different problems, but it won't be a big problem. Won't be worth as much as the others. Just figure out what is the tau, what is the V, what is the A. All right.